Hello everyone, thank you for attending this presentation. I will present you some work I did with Nutan, Limaye and Srikanth, Srinivasan. We will show that some explicit polynomials cannot be computed by polynomial size constant depth algebraic program. We want to study polynomials, so if we consider P like that, we can notice this expression. It is given by a sum which has 2 to the n terms. So if we want to compute this polynomial P like that, we'll need 2 to the n operations. But we can also notice that the same polynomial P can also be computed by a product of the 1 plus xi, and the product is just of linear size. So we can compute it with only a linear number of operations. And so we can ask how many operations are needed for computing a given polynomial. So informally, in fact, the result we will present today, it is there exists an explicit polynomial h which cannot be expressed of the following form. What is this following form? It is a sum of linear size of a product of linear size, and so on until a sum of linear size of product of linear size. Yet at the end, there are only Tij, which are constants or variables. The main point here it is we assume that the number of alternations between sums and product is constant. More formally, we want to introduce a new model of computation for the polynomials. They will be called algebraic circuits. So what is it? It is a directed acyclic graph where the vertices are labeled either by arithmetic operations, addition or multiplication, or for the input nodes by variable or constants. We'll mainly characterize the complexity of this model with two parameters. First, the depth. So it is the longest path from an input to the output. For example, here it is 3. Moreover, it is always possible to consider circuits where the operators alternate and where the top node is an addition, like in the example, so we'll always do that. And so we'll call such a depth 3 circuit a sigma pi sigma circuit. Second, the other parameter is the size of the circuit, which is the number of operation nodes. Finally, in the particular case where the underlying graph is a tree, we'll call such a circuit a formula. What was known before? In fact, for Boolean complexity, even exponential lower bounds against constant depth circuit have been done since the 80s. But in algebraic complexity, there are far fewer results on the subject. Let us consider depth 2 circuit. So such an expression is just a sum of monomials, and the only liberty that we can have is we can add useless monomials to retract them after. In particular, the minimal size we can get is the number of monomials. And for the polynomial we saw before, with an exponential number of monomials, we can conclude that it needs an exponential size depth 2 circuit. Now in depth 3. In depth 3 you consider sum of product of sums. And here the best result we had, it was a result I shown with Kayal and Sarah, that there are polynomials which needs at least an almost cubic size to be computed by a constant depth circuit. In depth 4, a recent result shows that we can have a lower bound in n to the 2.5. And for larger depths, the best we knew were superlinear lower bounds. Consequently, in algebraic complexity, as soon as the depth is at least 3, it seems we are far to get superpolynomial lower bounds. We can ask what is the reason of this difficulty? What is the reason why it seems we are really weaker in arithmetic complexity than in Boolean complexity? In fact, there is an essential result by Valiance, Kuhn, Berkovits, and Rakov, which shows that for arithmetic circuits, when we want to compute a polynomial of polynomial degree, then we can always reduce to a circuit of logarithmic depth, while remaining of polynomial size. Finally, if we want to parallelize even more to obtain a constant depth, we can do it with a size smaller than n to the d, that is to say better than with a trivial transformation. In particular, if one obtains fully exponential lower bound in n to the d for constant depth circuit, as it is done in Boolean complexity, it will directly imply superpolynomial lower bound for general circuit. So it seems a very difficult task. Here, our bound will be of the form n to the d to the something which decreases exponentially fast with the depth of our circuit. In particular, when the depth delta is constant, it gives a bound in n to the d to the some constant. So what is the explicit polynomial P and D? So in fact, our R polynomial will be IMM. What is IMM? So IMM stands for iterated matrix multiplication. So let's take D matrices. In the first matrix x1, we put n square variable. So each matrix of size nn. In the second matrix, we take n square new fresh variables, and so on. So at the end, we'll get d times n square variables. We do the product of these matrices. We take the 1-1 entry of the product. And so this will be our polynomial. So in fact, we can reformulate our result. We want to show that this polynomial, IMM cannot be computed in a polynomial size with constant depth circuits. I just want to present you some other results which we can get from the main result, but I will not focus on it after. So one consequence, one corollary of our result is what we can get for polynomial identity testing. So in fact, if we know that a polynomial is computed by a constant depth, and we have black box access to this polynomial, and we want to deterministically determine if this polynomial it is identically zero or not, we can do it in subexponential time. So in fact, this is better than what was done before, because for example, just for depth 3 circuit, before the time it was n to the k, when the k was the first fan-in, but the first fan-in can be linear and it will be exponential in n. And but in fact, so this result is just a corollary of what it was known. In fact, there are a lot of results which is known between the relation between hardness and randomness. And so if we just plug our result in this literature, we get exactly this subexponential time PIT. Another result I just wanted to mention, it's we can even get a depth hierarchy theorem. It means, in fact, for any depth gamma, we can find a polynomial which can be computed in depth gamma in size s, and such that if we want to compute it in depth gamma minus 1, so just we decrease depth by 1, we need a superpolynomial size with respect to s. So back to our main result, so we want to show that IMM cannot be computed in constant depth in polynomial size. So we'll do it by escalation. So in fact, we want to consider weaker formulas. So we'll need to consider different models of formula. So in fact, we can first look at restriction of polynomials. So first restriction, a polynomial will be called homogeneous. So that probably is everyone know. It means that every monomial has same degree. A polynomial will be called multilinear if every monomial has a degree at most 1 in each variable. Finally, what will be the main point, the main restriction we consider, it is a set multilinear polynomials. So in fact, if we have a partition of the variable belongs to the sets x1, x2 until xd, a polynomial is called set multilinear if each monomial is of the form one variable from x1 times one variable from x2 times one variable from x3 and so on until time one variable for xd. For example, if we look at our polynomial IMM, each monomial where we can notice that each monomial is of the form there is one variable which comes from the first matrix, one variable which comes from the second matrix, and so on until one variable which comes from the last matrix. So it is a set multilinear. And so if we have a restriction for polynomials, we can deduce from that restriction for models of computations. So the natural way to have a restriction for the models, it is, so we say a formula or a circuit, it will be called homogeneous. If in every gate, if at each step of the computation, we compute something which is homogeneous. So in particular, we can only compute homogeneous polynomial. But in fact, if you want to compute a homogeneous polynomial by a homogeneous circuit, it means that at each step, each intermediate step, we are only allowed to compute homogeneous polynomials. We can do the same for multilinear, and in fact, we can do the same for set multilinear. So if we want to compute a polynomial which is set multilinear, we can say that at each step, we are only allowed to compute a polynomial which is set multilinear. So we will consider in an intermediate step, probably the degree will be smaller, so we'll only consider a subset of the partition, and we want to be set multilinear with respect to this subset. So what's interesting now with these restrictions, in fact, Raz showed, so already more than 10 years ago, that if we can compute a polynomial by a formula of size s, and our polynomial p, it is set multilinear, then we can compute it in a set multilinear way with a blow-up in size, but the blow-up, it is just something in log s to something exponential in d. In particular, something which is interesting, it is if we consider a small degree polynomial, but take degree log n divided by log n. And in fact, we can notice in d, it is in this setting, in fact, this, the log s to the big of d, becomes polynomial. In particular, it means that if we have a polynomial size circuit computing p, it implies a set multilinear formula computing p of size poly fn. So what is interesting in this transformation, in fact, it is the opposite side. If we can show that some polynomial cannot be computed by set multilinear formula in polynomial size, then it shows that we cannot compute this polynomial by a generic formula be careful, RAS transformation doesn't work for constant depths. So here it seems that there is a problem for us, because if we start with something which is generically of constant depth, in the RAS transformation, it seems that we can get something which is set multilinear, but not constant depth anymore. So it seems hard to be used for us. So the first study is to transform RAS proof to get something similar, but for constant depth. And in fact, that is doable. In fact, we showed that we can show that we can transform a formula of set f of depth gamma, if we want to compute the polynomial which is set multilinear, by we can homogenize this formula in depth 2 gamma minus 1. If gamma is constant, 2 gamma minus 1 is still constant. And the blow up in the size is something just exponential in D. This transformation needs characteristic 0. In fact, it was already known for depth 3. It used Nutan identities. And so, in fact, we just show that we can generalize this result for any constant depth. In the second step, we want now to transform homogeneous formulas into set multilinear ones, and we can show that we can do it. Here we don't need to modify the depth, and the blow up in size is always multiplied by something which is exponential in D, only exponential in D. In fact, this step is it seems it was not known before in the literature, but is nothing really interesting. It's really the trivial approach. We want to do something a trivial way, and it works. And so what is interesting is if we want to go in the other direction, it shows that if we can show that some polynomial cannot be computed by set multilinear formula of depth 2 gamma minus 1, we need size at least n, something which is superpolynomial in n. It implies that it's the same for homogeneous formula, and it implies it's the same for general formula of size gamma. We can get some superpolynomial lower bound. Just one point here, so we have the first transformation here which needs characteristic 0, and in fact it is the reason of the constraint of the characteristic 0 in our main result. The only point where we need characteristic 0 is here. If we can avoid the restriction here of the characteristic, it will avoid it in the general result. So it's good news. This is very good news, because in fact, to get the superpolynomial lower bound for general formula of the depth gamma, we just need lower bound for set multilinear formula of some depth. And that is good news, because we have a lot lower bounds against set multilinear formula. And in fact, for example, a lot of work after RAS, based on RAS work, shows that exponential set multilinear lower bounds. But the problem it is, most of the lower bounds are of this form. It's something which is f of d, so f in general something which is exponential. So lower bound is exponential in d times poly of n. But that it doesn't work for us, because we have a blow up in d to something exponential in d. So if the lower bound is exponential in d, we have nothing more. In fact, for escalation to work, we need the lower bound of this form, n to the omega of f of d. And unfortunately, what was known in RAS work, it does not seem to imply something like that. So we need to find such a lower bound. We call it non-FPT lower bounds, similarly to what it is known in amortized complexity. So in fact, we want to show that if we want to compute IMM in depth delta, by a set multilinear formula, we will need size at least n to the d to the something exponential. Okay, so just to show the plan of the proof. So if we can get this lower bound with the efficient conversions and with the escalation, it will imply our main result. Okay, so we just want to focus on the set multilinear lower bound. The second point, I say that in fact in the literature, for depth 2, it was known, superpolynomial lower bound, it's trivial, but the first case where it was not known, it is for depth 3. Donc for gamma equals 3, if we can get superpolynomial lower bound for depth 3 circuit, it is first case interesting. And gamma equals 3 means for set multilinear we are interested, so it's 2 gamma minus 1 is delta equals 5. So the first case we are interested, it is lower bound for set multilinear depth 5 circuit, computing IMM. If we want to compute IMM, delta equal 5, so with a sum of product set multilinear formula, in fact we will show that we get the n to the square root of d lower bound, which is in fact optimal. Because in fact, by Gupta, Kamat, Kayal, Saptaishi, we know that we cannot do better than n to the square root of d. So what will be the techniques? So it is a typical lower bound proof. So what is the idea? We want to find a measure mu. to measure the complexity of subpolynomials. We want to show that the measure is large for our hard polynomial, and the measure is small for something which is computed by a small set multilinear depth-5 circuit. So what will be the measure? In fact, the measure is the famous one, which was already introduced by Nutan and Srinivasan in 1995. So let's partition. So we are computing a set multilinear polynomial. So let's partition the variables, the sets of variables into two parts: the variable on the left and the variable on the right. And ML will be all the multilinear monomials over the left variable, and MR all the multilinear monomials over the right variable. And then set multilinear for both. So if you put all the set multilinear monomials on the left as an index of a matrix, of the rows of a matrix, all the set multilinear monomials on the right as indices for the columns of the matrix. In fact, if I have a polynomial f, we'll put in this matrix, in the cell m1, m2, the coefficient of f in front of the monomial m1, m2. And so the measure of f, what we call it the partial derivative measure, is just the rank of this matrix. This measure has two good properties. The first property, this measure is subadditive. It means that the measure of f plus g is always smaller than the measure of f plus measure of g. In fact, that is just the fact that the rank is subadditive. But what is also interesting is here, in the case of the polynomial are set multilinear, so in our case, this measure is also multiplicative. Mu of fg equals mu of f times mu of g. So we say the first point we want our measure to be large on our hard polynomial. So let's focus on IMM. So IMM, we can write it. It is we have to find, in fact, one path from 1 to 1, going by the D matrices. So it will be the sum of all monomials of the form 1 x. We take the input of coordinate 1 I1, after I1 I2, after I2 I3, and so on. Let's take, so in the partition of variables, so we say our partition where each set of variables were variable from the first matrix, variable from the second matrix, and so on. Let's take, we put on the left all matrices which with odd indices, and on the right every matrices with even indices. In particular, if we want to look at what is the coefficient in front of the coefficient m1, m2 in IMM and D, so what is of the form of m1, m2? So we know that m1 is something we only consider a variable on the left. Variable on the left with corresponding with matrices with odd indices. So with odd indices, so we have to take something in the first matrix. So first matrix we have x1, 1, I1. After we have to take something on matrices, so in the third matrix, x3, a2, and 3, and so on until the matrix d minus 1. For the monomials which index the columns, we have to take monomials with corresponding with even matrices. So we have to start with the second matrix, take index g1, g2, the fourth matrix, g3, g4, and so on until g minus 1, 1. And so we are testing the coefficient in front of this monomial. And in fact, so this monomial, we know for IMM, the coefficient is either 1 or 0. In fact, it is 1 exactly when this vector I1, I2, id minus 1 equals the vector g1, g2, g d minus 1. And it is 0 otherwise. In particular, this matrix, it is a permutation matrix. So if it is a permutation matrix, what we know that the rank is full. It is n to the d minus 1. So in fact, that was known already from the work by Nutan and Srinivasan. In fact, they apply this result to show that we cannot compute this polynomial with depth-3 set multilinear formula. If we want to compute something with a depth-3 set multilinear formula, so it is something a sum of product of sum. So the Lij are homogeneous linear polynomial over the variables. What we know that the measure of one homogeneous linear polynomial, so in fact, as this set multilinear, this homogeneous linear polynomial has to get only variable from one set. So it means there are two cases. Either this set is one set from the left, or it is a set from the right. In all cases, if it is a set from the left, it means on the right there is no set. In particular, the column has only one column. It's a column matrix. Or maybe it was a set on the right. So in this case, the corresponding matrix is only a row matrix. So it is the matrix associated matrix is either a row or a column. In particular, its rank is always at most 1. So now after we can use the properties we know about our measure. We know the measure is multiplicative. In particular, the measure associated to the product of the linear form.
the product of one, it's always at most one. Product of one, it's a product of something smaller than one, it is always smaller than one. And now we also know that the rank is subadditive. In particular, the rank of our polynomial is at most S. So if we want to compute something by a depth 3 circuit, sum of product of sum, we know the size has to be at least the rank of our polynomial. For IMM, we showed that the rank it was exponential n to the d, so it means that the size has to be at least exponential. It has to be at least n to the d. So we have already a lower bound for depth 3, semi-linear formula for IMM and d. So we say what we want to get is the same thing, but for depth 5. So we have depth 3, we can say what we can do similarly for depth 4. But in fact, for depth 4, there is something interesting. If we look at the polynomial we call product of inner product, so in fact, here we compute some inner product, a sum of one variable divided by some other variable, and we do the sum. And we do product of this thing for different new sets of variables. So in our setting, we say we already consider sum at the top, so that corresponds to sum of product, so it's what we call the 4 multilinear formula. And in fact, this we can easily notice that the associated matrix is also a permutation matrix. In particular, the rank for PIP is full. In particular, depth 4 multilinear formula can compute full rank polynomials. And in particular, it was the reason why it seems that the idea to use this measure was insufficient to get some interesting lower bound. Because it worked for depth 3, but for depth 4, already we can compute something which has the measure is maximal. So it was the reason why, in fact, there are a lot of work after to modify this measure. For example, the main success was with a shifted partial derivative measure. And in particular, in this way, there are some work to show some lower bound for depth 4 multilinear formula. For example, for IMA, we know that it is at least of this size. And there are a series of work using this measure or similar measure like that. But it was for depth 4. It seems that nothing like that. We are never able to get something for depth 5 multilinear formulas. And so the idea of this work, the main idea, in fact, is instead of using shifted partial, we will use something a bit different. We'll use to say different set size. In fact, so we have knows our polynomial is set multilinear, so our variables are partitioned into different sets. And until now, we always implicitly use the fact that each set have the same size. And for example, in our example in depth 4, for the product of inner product, what we wanted to do is to associate each variable here with another set here. We do the inner product, and so on. We take the second one here and the second one here, we took the inner product, and at the end we do the product of these things. But that only cannot work here. If we force this set on the left to be large and this set on the right to be small, we cannot do an inner product between the first set here and the first set here. So the counterexample for depth 4 is not working anymore. So for we'll see after. Let's focus. So we take on the left t sets of variables, such that the size is each set have size 2 to the k. On the right, we have a d minus t sets, and the size of each set will be 2 to the l. So at the end, we really have d sets as we wanted. So we'll say on the left, we'll take a large set, on the right, small set. So we'll say, let's take k larger than l, and we'll not want to take l really smaller. So we'll just say that l will be always at least larger than k divided by 2. So the first thing, we want to get something which has high rank. We want the associated matrix as high rank. And we know the number of rows is the number of submultilinear monomial corresponding to the set to the left variables, and the number of columns is the submultilinear monomial corresponding to the variable on the right. So we still want to get something with high rank, a matrix which is almost square. So we want the number of rows is similar to the number of columns. So in fact, we want to ensure that it is the same number. So we want the same number of rows and columns. So that implies what? So the number of submultilinear monomial from here, we have to take one variable from here, one variable from here, and so on. So we can take, we have 2 to the k choice to the t. So we have 2 to the kt, and here we have 2 to the l d minus t. So to get the equality, we just need to choose kt equals d minus t l. So finally, now we have all we need to get our result. So we have sets of variables of different size. We have a hard polynomial. We have a measure, Nielsen-Wigderson measure. We know that the measure is large for our hard polynomial. And so the question it is, what about the measure for a small submultilinear depth 5 circuit? So what is a depth circuit? Just to give the idea of the proof. So it's a sum of terms. Each term we call f a term, and the term, it is a product of the different factors. So the factor fj are depth Swiss multilinear formula. So we can look at each fj correspond to pj sets of left variables and qj sets of right variables. Okay, so if we can show that the measure of one term is smaller than a full rank divided to n to the square root of d divided by 100, it implies by subadditivity of the measure that the measure of all, we do the sum of all the terms, it will be multiplied by at most the number of the sum. So it will imply, if we want to compute something which is full rank, it will imply that the sum has to be size at least n to the square root of d, and so it's a win. So it's sufficient to get this inequality. And in fact, if you look at this fraction, the upper term, upper part, in fact, it can be written like that. So 2 to the kt, it was the number of rows. We had a matrix with the same number of rows and the same number of columns. And so we can say that the number of rows equal the geometric mean, which is the number of rows and the number of columns. And this good point of view, it is in fact, you can convince yourself by doing the computation that this geometric mean, it is equal to the product of the geometric means for each fi of the geometric mean of the number of rows and the number of columns of each fi. And secondly, we know the measure is multiplicative. In particular, the mu of f equals the product of the mu of fj. Okay, so in fact, to get the result, it is sufficient to show either there is one fj such that the measure is far to be close to the geometric mean between the number of rows and columns, or at least all the fj are a bit far to be equal to the geometric mean between the number of rows and the number of columns. Okay, in the first case, we can maybe say there is a fj with large degree. So in this case, it's a big win, because we know in all cases the measure of a depth 3 is always small. So here we have fj, which is supposed to be a good part of the measure. We know this measure is small, so in fact it will be already far enough to the goal. In the second case, all fj has small degree, and here we want to show that all fj are a bit far of the geometric mean between the number of rows and the number of columns. In fact, the idea is we know that all the pj and qj are integers, and they are small. So in fact, we just want to ensure that the number of rows and number of columns are really distinct. In particular, the rank will be at most the minimal of both of them, and so it will be distinct to the geometric mean. So in fact, we just want to choose k and l, such that we are sure that these two values are quite distinct. In fact, this is not very hard, because if you look at the ratio, you just need to look at kpg minus lqj and say that we want to be far to be 0. And so you just want to find k and l, so a fraction, a number, a real, such that we cannot approximate it by a qj divided by pj, which is the rational. And for that, we can use some result on your function in approximation. So with that, it directly implies that we cannot compute IMM in a depth 5, or we need at least size n to the square root of d. And with the escalation, so it implies that with general circuit, we also need n to the square root of d. In fact, with similar arguments by some induction, we can get the same thing for constant depth, set multilinear circuits, and so constant depth general circuits. So thank you. So for now, we can still have new questions. So the first thing is, can the lower bound be improved? For example, we get something in n to the d to something which exponentially decreases with delta. Can we get only something in n to the d to the 1 divided by delta, which is, I guess, the supposed bond? Secondly, can we improve the escalation? For example, can we remove the characteristic 0 restriction? I said it just appeared in the transformation between general circuit to homogenized circuit. So can we gain something here? We saw that the lower bound implied an efficient PIT. Can we get anything for construction? Similarly, in a similar way, can we transform our lower bound to something for algebraic proof system? And finally, something I think maybe more interesting, it is after the first measure by Nissan and Vidason, there was a different version of the measure to get better and better bond. So finally, here we come back to the initial measure. It's possible to modify it to improve the bonds. Thank you.